Have you ever wondered why things in the universe can be so, well, stubborn? We're about to unpack the fundamental rules of motion, and it all comes down to that stubbornness. This is the very bedrock of physics, so let's get into it.
You know, it really all starts with something you've done 1,000 times. You walk up to a shopping cart. It's just sitting there. You give it a little push, it starts to roll. You push it harder, it goes faster. Seems super obvious, right? But the physics behind this one simple act is actually the same physics that governs everything from a tiny rolling marble to planets orbiting the sun.
But that brings up some pretty big questions. I mean, why does that cart stay put until you push it? What's the real relationship between how hard you push and how fast it goes? And what are all the invisible forces happening all around it? Let's break that down.
To get started, we have to understand this core property of the universe, something scientists call inertia. But honestly, you can just think of it as cosmic laziness. Turns out, objects just don't like to change whatever it is they're doing.
For a really long time, people, even brilliant minds like Aristotle, they just assumed that things naturally want to come to a stop. It makes sense, right? But then Galileo came along, and he discovered something really profound. He figured out that an object in motion, kind of like this ball rolling here, actually has a natural tendency to just keep on going forever, unless some outside force gets in its way.
All right, let's try a little thought experiment. Picture a car zipping past you, and it's got a box sitting on the roof. From where you're standing on the sidewalk, that box and the car are like a single unit, just cruising along at the exact same speed. They're in the same state of motion.
Okay, so what do you think is going to happen if that driver suddenly slams on the brakes? The car itself is going to grind to a halt, obviously. But what about that box? Remember, its lazy tendency is to just keep doing what it was already doing.
And whoosh, there it goes. The car stops, but the box doesn't. It just keeps on moving forward because, get this, nothing has actually acted on the box to stop it. It's resisting that sudden change. It's trying to keep its velocity, and that resistance, that is the heart and soul of inertia.
Now here's the really cool part. It's not just things in motion that are stubborn. Things that are just sitting still are stubborn too. The dishes on this table, they want to stay at rest. If you yank that tablecloth out fast enough, you're not actually applying a force to the dishes for long enough to overcome their own inertia, their own desire to just stay put.
So, this brings us to the big one, the formal rule from Sir Isaac Newton himself, his first law of motion. All those examples we just saw, the shopping cart, the box on the car, the fancy dishes, they all follow this one beautiful, elegant principle. An object is just going to keep doing what it's doing, whether that's sitting still or moving nice and smooth, until some kind of push or pull from the outside comes along and messes things up.
Now that phrase, unbalanced external force, that's the key. So let's jump to our next section and see how this all builds. We've got to understand what makes a force unbalanced. And the best way to think about it is like a giant cosmic tug of war.
So here's the crucial difference. When forces are balanced, meaning they're equal and pulling in opposite directions, they just cancel each other out. The total force, what we call the net force, is zero. So nothing changes. But when the forces are unbalanced, you've got a winner in that tug of war. The net force is not zero, and that is what causes the change in motion. That's what makes things speed up, slow down, or change direction.
This little table here makes it crystal clear. So in that first row, you've got 20 newtons of force pulling left and 20 pulling right. They cancel out. Net force is zero. No change. In the second row, both forces are ganging up and pulling to the right, so they add up to a 50 newton net force. And in the third, that 30 newton force to the right easily overpowers the 20 newton force to the left. In both of those last two cases, because the forces are unbalanced, you get a change in motion.
Okay, so we know an unbalanced force is what we need to change motion. But how much force do we need? Well, that really depends on just how stubborn the object is. And an object's stubbornness, its inertia, is directly connected to its mass. The principle is actually pretty simple. More mass just means more inertia. It's a straight-up cause and effect relationship. I mean, this is exactly why it's so much harder to get a full shopping cart moving than an empty one, and why it's a real pain to try and stop it once it's rolling downhill.
And this bar chart, wow, this gives us a dramatic, real-world look at that idea. I mean, look at the difference. They're all going the same speed, but that massive 80,000 kilogram truck has so much more inertia that it needs more than double the distance to stop compared to a regular car. Its tendency to just keep on moving is absolutely huge.
Now, this isn't just some abstract physics concept. Understanding these laws has led to some incredible technologies that we use every single day, and a lot of them are designed to keep us safe. So let's see how this all connects back to your life.
Hey, remember that box flying off the car roof? In a car crash, that's you. The car stops instantly, but your body's inertia wants to keep right on going, maybe through the windshield. A seatbelt is literally a life-saving application of Newton's first law. It's designed to provide that critical, unbalanced external force that changes your state of motion and makes you stop right along with the car.
Ever use cruise control? Guess what? You're using Newton's laws. To keep a constant speed, the net force on your car has to be 0. Cruise control is this brilliant little system that's constantly adjusting the forward push from the engine to perfectly cancel out all the backward pulling forces, like air resistance and friction. The forces stay balanced, so your speed stays perfectly constant.
And how about for fun? An air hockey table is literally engineered to take advantage of inertia. By pushing that cushion of air up through all those little holes, it gets rid of almost all the friction. That's the force that wants to slow the puck down. With almost nothing to stop it, the puck just glides in a nearly perfect straight line, just obeying its own inertia until something else comes along and hits it.
So you see, from shopping carts to seatbelts, these rules are just fundamental. And this brilliant little device, Newton's cradle, it actually demonstrates all three of his laws at once. We've focused on inertia, why that end ball wants to stay put until it's hit, but it also perfectly shows how forces create acceleration, and of course, that famous idea that for every action, there's an equal and opposite reaction. It's the entire story of motion in one neat little package.
So, I'll leave you with this one final thought. Now that you understand the law of inertia, this fundamental stubbornness of stuff, what are you going to start noticing out there in the world? The next time you see a ball roll to a stop or feel yourself lean when a car takes a sharp turn, you'll know exactly what's going on. The rules are playing out all around you all the time.